Well, David's talk was a very interesting and useful introduction to many of the things I'm going to say, particularly some of the data problems that one can encounter. What I'm going to talk about is a new class of time series models that we developed in the spring of last year and have subsequently extended in ways in which I'll describe. But essentially, what these models do is they're time series models for predicting a variable which, when cumulated, is subject to an unknown saturation level. And in fact, I'd written a paper on this many years ago, and it was concerned with new products entering a market and the fact that there was a saturation level for many of them. And when COVID struck, my colleague Paul Catterman was working for Public Health England, east of England, and making forecasts. So I started looking at this literature and applying it to COVID. And as the pandemic progressed during April and May, that model got developed considerably to adapt to what was happening. One of the good things about the pandemic is that with daily data, you get a pretty good indication, a pretty quick indication of when your models are going wrong and when your models are going right. So as I say, these models are actually relevant for other areas apart from pandemics, but that's what we're interested in at the moment. So they're going to be able to make forecasts of the number of cases or deaths, the growth rate, and also we can make nowcasts and forecasts of the instantaneous reproduction number, the famous R number. And these methods are basically classical statistical methods. So estimation is by maximum likelihood, and we're using standard goodness of fit procedures to assess how good they are. It's important to mention this because most of the papers in epidemiology, for example, estimating R, were not using these kind of methods. They were using, well, sort of Bayesian methods. I say sort of because, well, you better read them to see what was going on. They also contrast with some of the main models that they've been using in epidemiology, which usually go by the name of semi-mechanistic Bayesian hierarchical models. So those are models like the Neil Ferguson's team at Imperial, for example. And those have been standard kind of models in epidemics. You never quite know what's going on in these models, though, whereas our models are relatively simple and we think they're transparent. You know, you can see exactly what's going on. And they're using historical data to make forecasts rather than doing it by simulations, which is what the epidemiological models do. There's a nice paper here in Journal of Economic Perspectives that contrasts the two kinds of approaches, and of course it's the same as in economics, where you get DSGE models and more classical time series models. The models are used for different purposes to some extent, so they're not directly comparable, but they both have the roles. So what our models are called structural time series models. So they're based on unobserved components, but they're paying attention to and they're respecting what prior knowledge we've got. So with epidemics, we do have upper bounds, and those upper bounds, breaks on the system in classical models come about because everybody's getting infected, but as we know in the last year or so, it's come about because of behavioral changes, policy changes like lockdowns and so on. So we've got to be able to adapt to those changes. We can use those for policy evaluation and counterfactuals. So we'll be seeing later how we can use it for assessing things like the what Sweden did in the spring of last year. So the main papers are, the first one that Paul Catterman and I wrote came out in the Harvard Data Science Review in August. And then subsequently we wrote one on estimating R, which I think is coming out in one of the scientific journals, so keeping our fingers crossed on that one. And then there's a couple that came out of conferences at the National Institute of Economic and Social Research. So what I'm talking about today is really an amalgam of these various papers. So I'll talk initially about the univariate models and the rationale behind those. Then I'll talk about tracking R. I'll then talk about leading indicators and how those work. And then finally, I'll talk about control groups for Sweden. So we're going to let YT be the daily number of cases or deaths or whatever it is. And big Y is the cumulative amount, the total amount you've got. So obviously YT is the first difference of big Y. We don't actually model either of those directly. We take the logarithm, but in fact, what the growth theory tells us to do is take the logarithm of the cumulative series. So we're taking log GT, where GT is the growth rate in the cumulative series. So it's the growth rate in the total number of cases or the total number of deaths. And growth curve theory tells you that in the standard epidemic that goes up and down and doesn't come back up again, log GT follows a downward time trend. Of course, as we know, with second and third waves, that hasn't been the case. So we're going to need models that are going to be able to adapt to these recurrent waves. And they're going to be able to change in policies, behaviors, new variants, and so on. So this is data FL is Florida, okay, which I'm going to turn to later on. This shows the total number of cases in Florida. They were the first in there with the second wave. They had an initial wave, lockdown for a month. It then all went down, and then boom, it shot up again. The point to notice here is this is the log of Florida cases, and this is what we call LDL. This is the log of the growth rate of the total. And you can see you've got this downward movement in this first wave. Whereas if you just take logs, it goes up and then down. So there's whole literature on growth curves. The one we started to hit on some weeks into the epidemic was the Gompertz, because this in fact comes down slower than it goes up, which was clearly happening in March and April of last year. And what that theory tells you, if you look at a Gompertz growth curve, is that the log of GT in continuous time is going to be a downward time trend. So gamma there is negative. And clearly you could put that into a regression model and estimate it by OLS. Okay, fine. And that worked for a time, but of course it doesn't work once new policies come in, new behavior comes in, new variants come in, and so on. But it does work for a while. This is the log of the growth rate for the UK in Italy last year. So it's starting off in, that's from end of March, early April, down to mid-June. And you can see that actually they're not far off being a linear time trend. They're not quite a linear time trend, but they're pretty close. You can see here the day of the week effects, which David referred to, which one has to say can be a little bit tricky at times, particularly with public holidays, which mess up this pattern even more. Okay, so we have the growth curve theory tells us that we should have this downward trend, but it's not going to be deterministic forever, because we know trends in most things are not deterministic. I was quite horrified in David's talk when he mentioned the Office for Publisher Responsibility had got what was essentially a deterministic trend model. And as he showed, it doesn't work. So here, what do we do? Well, we've got the time trend, and we want to make that stochastic. And we can do that very easily by adding shocks to the level and shocks to the growth rate. What we ended up doing, though, was suppressing this shock here. And what it means then is that the trend here is at integrated random walk. So second differences are random. And what you can show is that when you've got that, if you have to do smoothing, and you're doing all this by the Kalman filter, by the way, then you'd get a smooth trend. It's actually closely related to a cubic spline. So the crucial thing here is the signal noise ratio, Q. When Q is 0, of course, it's a deterministic trend. So all of this is done in state space form, and initially we use the stamp package of Koopman et al., which is one of the options in Oxmetrics. We subsequently have written a package in R, and that's what we've been using in the NISER project, where we're tracking the progress of the pandemic, and we hope to make this available soon. This is just to say that if you're allergic to Kalman filters, you can always do this. There is a reduced form where you can just program up the recursions, but there's considerable advantages to actually doing the unobserved components form, because it gets prediction errors and so on. We can make forecasts of little y and big Y recursively. You don't need to worry about those. The point is, though, that as long as gamma is negative, then you will have a saturation level, which you can work out. And that's key, because when cases start to shoot up, usually there's something that comes in, changing behavior or policies, which start to try to pull it down again. This is an example. This is Germany, and what you can see how the model works here. So this is the end of March, and these are forecasts made on the 1st of April. And at this point, it's still going up slightly. It hasn't started to go down, but the model's actually detecting a slowing down in the growth rate, and it's actually then forecasting this downward trend, complete with the daily effect. If you've got small numbers, you probably want to go to negative binomial distribution. And if you do that, there's a way of doing that, which is called score-driven models. And there's a program, this time series lab, that will actually do some of these score-driven models. So we had a negative binomial model as well. And here is the negative binomial model in action. And I'm using deaths in the UK. And these are forecasts. These are unconditional forecasts going ahead. You'll see in this case they're slightly below what actually happened, and throughout May, I was fretting somewhat, because every time the new deaths figure came in, I was thinking, oh well, it's too high. What's keeping it high? It should be down here. But then what happened around about this point? They revised the data. So they revised the definition of a COVID death, So in fact, it was people who died within 28 days of a test, and all the numbers came down, and actually my predictions were really quite accurate. So sometimes data revisions can be a good thing. We can also use these curves to put in an intervention effect, and you can do this. We decided to use the cumulative distribution function of a logistic, and when we did that and modeled it, we got this. So this is looking at UK new cases, and it's going down there, and it goes down nice and smoothly. So it's a smooth trend coming down, and this is adapting to the first lockdown in the UK. I then tried to see what would happen if we we put that back by a week. Suppose they'd locked down a week earlier, what would have happened? Well, just pushing that intervention back a week suggests that you'd have been on this growth path. You end up back again on this one here. And from that, you can make an estimate of the number of deaths you might have saved by closing down a week earlier. Now, round about the end of May, June, there were about 40,000 deaths in the UK, and this suggests that had you locked down a week earlier, you could have halved that number. Interesting enough, Neil Ferguson of Imperial College came up with a very, very similar estimate. I'm not sure how he got it, but it's kind of reassuring to know that we were in the similar kind of range for that number. Okay, what about estimation of R? Well, epidemiologists use a variety of ways to estimate R. As I say, the sort of Bayesian methods are used. There's also more practical and transparent methods, such as those used by the Robert Koch Institute in Germany, where they adopt methods based on simple moving average, but they're taking moving average of the number of new cases, and as you can see from the graph, that's not a very good idea. I mean, you'd be better off to look at logs, but anyway, at least one knows what they're doing at the RKI in order to do that. So it's a good baseline. In our time series model, we do something different. We can get R out of the estimate, or the nowcast, if you like, of the current growth rate of the number of new cases. And that comes about from the model. It basically comes about from the nowcast of gamma. In other words, but nowcast just being, the signal extraction at time t, and the nowcast of G, which is the growth rate of the cumulative total. And that, in fact, is the exponent of the delta in the model. So you can pull that out of our model, and then you have to make an assumption about a variable called tau, which is the generation interval. So it's the time you've picked up the virus, but it takes tau days before you start passing it on. That's usually taken to be about 4 for COVID-19. Now, there's the paper by Wallinger and Lipsitch, which then says, well, if you've got the growth rate, then there's various formulae that you can use to get R. It depends on the generation distribution, but the bottom line is that the two we're likely to use are those 1 plus tau gy or exponential tau gy. So what we've seen from this is that the main change there is going to be gamma. The G's got less variability, but gamma is the key thing. So if we've got some measure of the variability of gamma, we can get some measure of the variability of gy, the growth rate in new cases, and hence we can get some measure of variability in R. So none of the other methods do this. They just produce these numbers. The estimates of these are going to depend crucially on Q, which is the signal noise ratio. We can estimate that by ML, or if we've got small numbers, we might want to impose a value from past experience. So something like 0.005 turns out to be pretty good. And the Kalman filter output tells us that at time t, or at the end of the sample, gamma t is normally distributed with a mean gamma t, which is the contemporaneous filtered estimate and its variance. So those are produced by the Kalman filter. So from that, we can get estimates of, well, the mean of R and its standard deviation. And we can work out statistics like the probability that R exceeds 1. So if you're coming out with a point estimate of R is equal to, 1.1, well, what's the standard error on that? I mean, can we be sure it's above 1, or is there only, say, a 60% chance that it's above 1? So this is important information to have. And in the NIESR tracker, we include those bounds, as I'll show you in a minute. We also include them. Paul Katterman has also done a tracker for India as well. So he does all the Indian states, and that's getting a lot of interest over there because it's producing estimates and forecasts, which are actually very useful for policymakers at the state level. So this is what we've been doing. We produced graphs like this for the NIESR, and these are our estimates of R together with a confidence interval. And you can see here, we respond quite quickly to the effects of the lockdown at the beginning of January. The dotted lines here show the estimates from SAGE, which is the committee in the UK that advises the government. And basically, they get estimates of R by all the epidemiological groups doing their estimates, and then they get the highest and they get the lowest, which is giving you this range. There is a delay in them doing that, whereas we can get our estimates pretty much immediately. And as we see, we react more quickly, and our confidence intervals are confidence intervals, whereas these are just the difference between the biggest and the smallest. I guess they're assuming that all these estimates are good ones, and that none of them should actually be thrown out. Okay, so the next thing I'd like to move on to is looking at multivariate methods and how we can bring together different bits of data. And that'll then lead me on to looking at leading indicators. So, for example, in the UK, they have two series. They have one which is the published data, so it's the data that comes out on a particular day. So the data we'd be getting about now on Friday would actually relate to what had happened on Thursday. There's also data which is according to the specimen date. So it's, you know, when they actually did the test. The trouble with that is when you look at it, the first three observations you have to discard because they're incomplete. They haven't got all the data in. So you've really only got the specimen series up to time t-3, whereas the published figure you've got at time t. But marginally, the specimen series is probably more what you want to get. The question is though, if you pull the two together, can you do even better? So you could construct a model. I mean, it's like models that have been used in econometrics. For example, way back, I had a paper looking at unemployment data and looking at the data from the quarterly survey and the monthly data from the claimant count. And the survey data was regarded as being better. It's measuring more what you wanted, but the claimant count you got much quicker. So how could you put them together? Well, the answer is you build a bivariate model and you use that to construct a good underlying estimate of the variable you want. And it's the same here. So we're working with the log of the growth rate in both cases. And the second one there would be the specimen data. So it's only available up to t-k, whereas I said k we've taken to be 3. And the point about that is we're assuming they're both on the same underlying common trend. So this is this non-stationary trend driven by an integrated random walk. I don't think I said before when I introduced this, the point about the integrated random walk, it's driven by shocks to the slope, and it's that's crucial. You want to detect these changing slopes so you can get these movements when the variable of interest is changing direction. So we assume that that's the same. There may be a constant term in there. And then we might want to add some stationary components, delta 1 and delta 2. And I've just put them here as simple AR1s. But it's this thing that's crucial, and that's what you're estimating, and you're using data on 2 series to do that. You could, in principle, bring in other data sources. I mean, for example, the surveys that the ONS does. You could throw that into the mix as well. Those are probably more accurate, but again, they've got delays. But you could do much the same as we did with the unemployment data. That's just a picture of how we've early on in January, we're doing predictions of the specimen data, but we're using the published data as well. So you can see the forecast and you can see the confidence interval, plus or minus 2 standard errors in that case. Okay, leading indicators. So I'm going to look at 2 cases essentially. And the first is Italy and the UK. And it's asking the question, given that Italy was ahead of the UK in the first wave last year, could we have used Italy to forecast what was going to happen in the UK? And the second case I'm looking at is new cases and deaths in Florida. This one's a bit tricky, trickier as we'll see. In other words, to what extent can we use new cases to forecast deaths? There's clearly going to be a lag there, and the relationship may actually change over time, but it doesn't mean that we should give up. We can still do something there. So all of these things involve our old friends, common trends, co-integration, and balanced growth. So it's non-stationary econometrics coming in there. Some of these ideas, particularly about balanced growth, it's a paper by myself and Steve Teal, which I'm going to allude to later when I look at the control group example. Okay, so this is a Gompertz growth curve, or rather it's the incidence curve, which is the first derivative of the growth curve. In other words, this is what's picking up the number of new cases or the number of deaths. So this, say, would be Italy. This might be the UK. This might be another country which has the same lag as the UK, but is bigger. So it's got more cases. Turns out that doesn't matter, because when you take the log of the growth rate, you get two parallel lines. So the bottom one here, or maybe it's the top one, but anyway, these two become indistinguishable. Yeah, that's what's happening. So this is the first one, and this is the lagging one, and the height doesn't matter. The line's exactly the same. So it's very nice in this deterministic case. You've got coming down parallel lines, and you can see the lag here, and you can work out the lag. Now, what's happening there is we're assuming the two gammas are the same. So gamma is a key variable. It's a key variable in the growth curve. And if you look at the UK and Italy, it appears that gamma pretty much is the same. So what we have there is the two series, and if G1 was Italy, G2 would be the UK. So you could think of a simple relationship there. And you've got that simple relationship because you've got balanced growth. They're both on the same downward trend on those parallel curves. But as it was said, trends are not deterministic, or they're certainly not deterministic for very long. We need to generalize to stochastic, and that's when we truly do have balanced growth, in the sense that if we take one series from another, then you get a stationary series. So you got a 1 minus 1 co-integrating vector. You could, of course, test for balanced growth using the KPSS test, because you're testing the null that you've got balanced growth. Okay, so looking at that, you think, well, actually, we didn't need to do all this prediction for the UK. We could just have used Italy. They're doing exactly the same thing, except about 2 weeks earlier. So if I lag Italy by 14 days, you can see the lines are one on top of the other, and that's the difference between one and the other. And most of that difference is due to the fact the daily effect in the UK is actually bigger than in Italy. And you can take that out of the model, of course. So we could do that. But what we're actually not interested in making predictions for the UK number. We don't care about the number of cases as such. What we care about is the underlying trend. So we could replace the log G1s, the Italy ones, by smoothed estimates, which would iron out the irregular movements, and use that. But it's actually rather better to set up a bivariate model. And if we set up the bivariate model, then we've got everything in one. So we can make future predictions for Italy, and the predictions for UK will then follow. So the all-in-one approach is going to work much better, much neater. So if we set up a bivariate model, what we would have is we can do it. The easiest way to do it, if you just have a single lag, would be just to create a new variable, which would be the lag, the leading indicator lagged. If you want to have a little distributed lag, you'd have to do something more complicated, but it's quite possible to do it. So you've got the leading indicator, you've got the target, and you've got this common trend here, which is the integrated random walk, and you've got the two AR1s. So it's essentially very, very similar model to the one we were looking at before with published and specimen data. And if you just set up that model, the leading indicator is K periods ahead. So you're pretending, if you like, that you've got observations up to T plus K, and you could then make forecasts for the target just by treating the missing observations, and the Kalman filter will fill in the gaps, and it will give you standard errors and everything. So in the bivariate model, what the filter's doing is it's implicitly weighting the observations in both series in order to compute nowcasts and forecasts for the target. Right, England, Italy in spring last year, dead easy because they're just moving down together. What about with waves? A little bit more complicated then. This is constructed actually for more recent data. It's just constructed artificially. I had a trend for England, and it was like this, and then I just shoved it back 14 days just to show you what's going on. So in the downward part of an epidemic, you know, they're more or less in parallel, but then they cross and then go up and like this. So it's a little bit more complicated in terms of the picture, but in terms of the model, it's fine. The model is going to deal with that because the model, remember, the stochastic trend is going to do these kind of things. It's going to turn corners. Okay, so we want to use new infections to forecast deaths a few weeks later. David Spiegelhalter on the BBC on 3rd of January said, well, just take 1/50th of the number of published infections 3 weeks before. And at that time, that wasn't a bad rule of thumb. But in fact, the problem with doing that is even before the vaccine came in, these relationships change over time. So in the case of Florida, for example, there was more testing and so on, and also the treatment of people in hospital changes. So fewer people die because treatments have got better. And of course, now we have the vaccine to throw into all the mix. Okay, but back to Florida last spring, pre-vaccine. As I say, Florida peaked in early April, they locked down in April, and then they eased restrictions, opened the bars and everything, and then bang, it shot up again in June. If you take a 7-day moving average, you get a clearer picture because it irons out these daily effects, and you can see sort of what's going on. This is new cases, this is deaths, which is behind it, and they're then doing that. So you can sort of see that, you know, the indication is coming in there. I mean, here's the turning point in cases, and there's the turning point in deaths, and then new cases start to go down here, where I think they must have locked down again. Deaths are still going up here, but then the question is, what's going to happen next? Well, here I've moved them forward 18 days. Now, having moved them forward 18 days, if it really was balanced growth, these two things would actually cross each other, but they don't. On the other hand, you can see that you are going to get some mileage from taking new cases as a leading indicator for deaths, because the turning points are matching up. So the long run relationships changing over time. We no longer have balanced growth. So what are we going to do? Well, what I've done is to put in a random walk component in the leading indicator. I could put it in the target as well. It doesn't actually matter which one I put it in. I could have a stationary component in the target as well, but I didn't do that. It didn't appear to be necessary. So the key thing is this, the delta. So that's allowing the relationship between deaths and new cases to change. In other words, you can move from deaths being, say, 1/50th of new cases to 1/100th of new cases. And of course, since the vaccine, that has been going down and down and down. I mean, new cases in the UK now, of course, are very high, but deaths are actually relatively low, nowhere near what they were like earlier on. And that, of course, is due to the vaccine. Okay, so this is the result of Florida. So this is the forecast. So it's the forecast made at this point. So this is deaths, the thick blue line, and it's still going up at this point. So if you're doing a univariate model, you'd be forecasting deaths for going up. Eventually, as it started to turn, we would pick up that with our model and it start to go down. But at this point, even our univariate model isn't predicting a downturn. On the other hand, if we put in the leading indicator, we end up with these forecasts, which are the ones in red. So before that, those are the smoothed estimates that have come out. These are the forecasts, and the green line is what actually happened. So deaths, in fact, were peaking here and then starting to come down. The purple dotted line there gives the underlying trend. So it actually works pretty well, but you've got to allow for the fact that you no longer have balanced growth. You're assuming that the growth rates are the same, but you're putting in that random walk component, so you don't have complete co-integration. Okay, finally, Sweden. Okay, so Sweden famously didn't have a full lockdown in last spring, but they still did things. I mean, you know, they recommended working from home, self-isolation if you felt ill, social distancing, and so on. And there was a certain amount of criticism at the time for them for not doing the full lockdown. So the question is, how many extra deaths might that have caused? Now, the way I'm going to do that is look at the growth path. You saw that when I looked at the UK-Italy example, Italy was actually a great predictor of the UK. There were, you know, once lockdowns had been imposed, you were more or less on the same growth path. So let's see what happens with Sweden. These are just the raw numbers, the number of deaths actually. UK, of course, huge daily pattern. Italy, of course, leading the UK by a couple of weeks. Sweden seems to be peaking here about the time of the UK. The numbers are much smaller, but as we'll see, once we take logs of growth rates, size doesn't matter. You know, there's no problem in comparing big countries and small countries. So that showed essentially now here's the logs of the growth rate. Again, I'm working with the 7-day moving averages, just so you get a clearer picture. We could do all the computations by putting in daily effects and so on, but I haven't done that. Really, the point I want to make is the point about these growth paths. So what's happened is, and until mid to late April, they're actually all on a very similar growth path. So Italy, I've shoved back by 14 days for reasons which I've already gone into, and then we've got Sweden diverge at the end of April. So Italy and the UK continue to go down in the same way, but Sweden starts to edge up. So this gap, the idea then is this gap here gives you some idea of what it costs Sweden in terms of deaths by not going on to a full lockdown in the way that the UK and Italy did. So doing a few sort of rather crude calculations, the overall conclusion was that between April 24th and July the 22nd, there were perhaps 40 to 45% more deaths than there might have been had a more stringent lockdown policy been adopted. It doesn't mean the death rate was higher. I mean, it was actually pretty comparable to Sweden and the UK, but then that's for other reasons. You know, Sweden might be more sparsely populated and so on. Now, these estimates are not necessarily what you'd get, what most people would have got, because if you looked at other Nordic countries, Denmark, Norway, and Sweden, sorry, Denmark, Norway, and Finland, their death rates were incredibly small. And people said, wow, you know, Sweden is 10 times as bad as, say, Norway. But that I don't think is correct. Now, given that these other countries don't have very big numbers, it's a bit hard to analyze them, but we've used Denmark, and which had the most. And if we look at Denmark, we can see actually it's on a similar growth path to UK and Italy and Sweden up towards the end of April. And then it's at this point where Sweden diverges. So that's all consistent with the story I was telling before, that there's perhaps other reasons why the Swedish death rate was higher than some of the others, which are not necessarily connected with lockdown policies. I'm not sure what the reasons are, but it seems to me that by looking at the growth paths, you get a lot of information about what went on. So basically we're saying, for reasons unconnected with lockdown, the death rate in Sweden was about 3.5 times that in Denmark, and the less stringent lockdown raised it to maybe 5.5 times. Okay, what other methods do you might want to use? Well, synthetic control. Synthetic control is the month at the moment. To me, what you should be doing, if you want control groups, you should be looking at countries or regions, whatever it is you're dealing with, which are on the same growth path until you get the event in question that you care about, and then you look at the difference. It's nothing to do with trying to match up a whole bunch of variables by a procedure which is essentially, rather sophisticated data mining. Anyway, having said that, there's a nice paper I'd show where he does use synthetic control, and the countries he comes up with are the usual suspects, as you'd expect, apart from Greece. Not sure how Greece gets in there, because all the others sort of places you'd expect. At the end of the day, he actually didn't get a very different result from the one that I got. But which in some ways is reassuring. But on the other hand, I wonder, he was using raw case numbers, standardized for population. I mean, if you take logs, would he have got the same results? I don't know. Maybe not. But the fact that the UK and Italy are able to track Swedish deaths so well in initial periods suggests that's a good way of doing it. So overall, I think the balanced growth approach to looking at controls is more appealing. It's simple and it's more transparent. And in the paper with Steve Teal, I get the same conclusion. It's worth looking at that paper just to see an analysis of some of the classic examples that were in the seminal papers by Abadi et al. And there's one or two of them, well, particularly the one about the effect of German reunification, which I think has serious doubt on the synthetic control methodology. And that seems like a good point at which to stop it. So thank you.